absolute value inequalities. So in this case, we already dealt with absolute value of A equaling B, assuming that B is bigger than 0, right? B is positive. And we said, well, this is either A equal B or A equals a negative B. That works. Well, what if that's not equal? What if it's an equality? If you see a less than or less than, that's the same rule. Keep in mind, you must isolate the absolute value first. So you want the absolute value isolated on one side, everything else on the other side. Then you say absolute value is less than. Then you would use that double called compounded inequality, double inequalities, if it's not included or included. And if you see a greater than, then you have to split it up, sort of what we did right there with the equal. One time positive, but when you put the negative, remember to switch the symbol. And that's pretty much it. So if I run to number 20, for example, the way I see it, you start reading this from the absolute value. This says absolute value of x, 3 minus x is less than. The absolute value is isolated by itself. And if this is bothering you, you could rewrite it. You don't have to, of course. And, well, this fits under that. Basically, whatever's inside the absolute value, to the right positive, and to the left negative. And there it is. And when I solve this, we're going to subtract 3 from each side. And when I divide by a negative, I switch the inequality symbols. Now, I forgot to mention, if somebody was to tell you, read what this says, well, that would be x is between negative 5 and 11. You wouldn't say x is greater than negative 5 and x is less than 11, which is what this is. You would say x is between negative 5 and 11. And since the direction was the same on all of those, 7 through 34, give us the interval notation, we're going to use, again, a graph, not part of the problem. All what I need to do is label those numbers. Keep in mind, you always start with the smaller and the larger. And the beauty of this, no matter how you do it, well, guess what? X is between, right there. Left to right, negative 5, running all the way to 11, not including either of those. That would be that problem. Okay, let me shift this to the left a bit. Here we go. So this thing could fit better. Alright, 22 is the next in line, and I look at that, say, wait a minute, well, look at that. X, absolute value of x is, let me think, greater than. I am going to switch those around. I'm going to do 24 first. And I added an example because I need to do more than one problem. So that goal is to isolate the absolute value by itself. What that means, you're going to eliminate 30. It doesn't matter what's inside the absolute value. You could clean that up. You could say that's 2 minus 3d plus, you could do that now, you could do that at the end. It makes no difference. So by subtracting 30 from both sides, that's negative 36. And it's not isolated by itself. There's still a negative 4 in front of it. So you divide by a negative 4. Absolute value. Since you divided by a negative, you switch the symbol, and that's a 9. And here you're looking at 6 minus 3d. And now, since I do have an absolute value on one side and a less than, I would say whatever's inside the absolute value, 9 and negative 9, and there it is. I would subtract 6 from each side, divide by a negative 3, and whenever we divide by a negative, we would say d is, we're going to switch that sign, D is between what is that? A 5 and a negative 1. And again, the graph is not part of this, but I'm going to graph it anyways. If I put this on a graphical, negative 1 is smaller, 5 is larger. They're both included, and simply between those. So negative 1 to 5. I'm going to do number 22 next and leave that example to the end. Why? Here we go. This problem is next. There we go. Odd how this works. So, here I notice that I have an absolute value on one side and it's greater than. So if I remember, one time I write it as I see it, like an equal, 2 minus 4x, literally as I see it. And one time I multiply this by a negative, 2 minus 4x. Since I multiply that by a negative, that's kind of not really how it is, but you could memorize it that way. And now you solve each of those. So basically you subtract 2 from both sides, divide by a negative 4, and whenever we divide by a negative, we switch the inequality symbol. There it is. Here I would subtract 2 from both sides, divide by a negative 4. Whatever you divide by a negative, you switch the inequality symbol, and this takes OR, and we did an OR versus AND on the previous set of problems. So this says x is less than or equal to negative 1. Assume negative 1 is right there, included. And this says x is greater than or equal to 2. And since it's an OR, well, the first solution, this runs all the way to negative infinity. From negative infinity to negative 1, this runs from 2 included all the way to infinity. And a union since there's more than one interval, and that's always how it works. And I'm adding an example. I want to do 2 of each. So here I notice, well, I need to isolate the absolute value by itself. One time as I see it. One time with multiplying that by a negative and switching the sign. And you solve each of those again. This is add 7 to both sides. X is greater than 13. Got it. Add 7 to both sides, or x is less than, if you add a 7, that's a 6. And if you put that on a number line, again, this says 13 not included, x is bigger than that. This says a 6 not included, x is less than that. So the same deal, negative infinity to 6 not included, 13 to infinity. To infinity, and a union since. So again, the graphical solution is not part of any of this. I'm adding that to make it easier for you to see how this works. Okay, now we continue on number 26. Oops, spelled the surprise. 26, we're looking at that problem. This is a quadratic inequality. Now students are tempted to factor, which is fine. I need those to subtract to get me a 7. 10 minus 3 is 7. That's perfect. Since that's the 10 and I want a positive 7, I want the 10 to be positive and the 3 to be negative. So that's 5x minus 3 and an x plus 2 being greater than 0. Now students are tempted to set this to be bigger than 0 and set this to be bigger than 0, and you can't do that, of course. Reason you can't do that, this is no longer a linear inequality. So if you look at inequalities, I was very specific when I wrote a linear inequality, meaning ax plus b is greater than a number or less than, but the power on the variables equal 1. What if it's not a linear inequality? Then you have two options. Either you graph this or you use a line test, and I'll show you what that means really quick. So one way of doing this is for you to think, and you don't need to graph it on 3 dimensions. So one way of doing this is for you to say, well, let's look at this. If this was a number line, this does equal 0. It equals 0 at -2 and at 3/5. So if this is the x-axis and the y-axis, I'm drawing a line that's hard to see because it shouldn't be there. If this was a parabola, wouldn't you say this parabola opens up because that number is positive? And if there are two x-intercepts, doesn't that indicate that the vertex is somewhere below and the graph looks like that? And if I want to know where is this graph bigger than 0, what does bigger than 0 mean? That means I want it to be positive. Wouldn't you say it's positive above the x-axis here and here? And in this case, you would say the solution is -infinity to -2, or from 3/5 to infinity. If you're not a big fan of graphing, then you really don't have to worry about that case. I'm going to show you another way of doing this. The way you do this, you would say, well, look, let's make a number line. There's the x-axis. We know this equals 0 at -2 and 3/5. And remember, you don't want to know the value, you just want to know the sign. If I pick a point in that region, let's say -3. If I pick -3 as a test point, -15 minus 3 is negative, -3 plus 2 is negative. If I multiply two negatives, that's a positive. If I pick a value between -2 and 3/5, let's say 0, test point. 0 minus 3 is negative, and 0 plus 2 is positive. Negative times a positive is a negative. And if I pick a point to the right of 3/5, let's say 2. 10 minus 7 is positive, and 2 plus 2 is positive. That product will be a positive. And since you want this to be bigger than 0, it's positive here and here, and that would be the answer. Now I'm going to continue the rest of the problems doing those both ways. If I could graph it, but if not, this will work. So when I look at this, I notice this is an inequality, and I need to get everything on one side, 0 on the other side. That's 5z squared plus 17z and a plus 6 being less than or equal to 0. So two options from here on. I would factor that. That is 5z and z. So that's 5 and 1. And if I take 3 and 2, or 2 and 3, well, it's this. 15 you add, plus 2, so they're both positive. 5z plus 2 and z plus 3. Again, I could do this graphically. Students don't seem to like that much if they're not good with graphing, but think about it as 2 dimensions, not 3 dimensions. So if I look at -2/5 and -3, -2/5 and -3. Again, I am aware this is a parabola that opens up, and since you cross the x-axis in 2 places, and it opens up, the vertex must be below, otherwise you wouldn't cross it. And if I want to know where is this less than 0, it's less than 0 right there. or right there. So the answer to this problem would be from, and it's included, right? So that would be -3 to -2/5. That would be my actual answer. If you didn't like that, you don't have to worry about that. You could create a line and you could say, well, let's see how this works. I'm going to pick a -3 and a -2/5, and I'll pick a value at this point right there. I'll pick -4. -20 plus 2 is -18. It's negative. That's all you care about. And a -4 plus 3 is -1. Negative times a negative is a positive. A point in there, let's say -1. -5 plus 2 is negative. And -1 plus 3 is positive. Negative times a positive is a negative. And a point to the right, you could say 0. Of course, you could plug it there if you want as well, but this is easier. 2 times 3, that's positive. And you want to know, where is this less than 0? It's less than 0 right there, and there's the answer. So graphing a parabola is something that we know how to do. This problem here doesn't work unless you want to graph a cubic, which you can, but we're going to learn that in this class later on. So I get everything on one side, 0 on the other side. And the greatest common factor between those is an x squared. That will leave me with an x plus 7. And -49, that will be an x plus 7. And if I factor this out, that is x plus 7 into x squared minus 49. If I take it a step further, factor completely, and I notice those are the same. Now we're going to learn how to sketch a graph of all of those. There's a whole chapter on this. Here I have to use a test line, and what I'm going to test is a -7 and a 7. So if I pick a point, let me put that right, can I put it right there on the right? Okay. If I pick x equal -8, this is always positive because you're squaring. You don't have to worry. So this is the only piece you have to worry about. -8 minus 7 is negative. That's a negative. A 0, this is always positive. 0 minus 7 is negative. And 8, that's always positive. 8 minus 7 is positive. You want to know, where is this bigger than 0? Isn't bigger than 0 meaning positive? And that happens to be from 7 not included because of this all the way to infinity. And if you wanted to get a quick sketch of this, again, we'll learn this later on. You're not responsible to know this. If I label -7, 7, and when x is 0, we are at -343. This is a cubic. So it runs left to right. This runs. The power is 2, and that's how the graph looks like. And you notice it's only positive to the right. Again, we're going to talk about that. You're not responsible to know this yet. And then we get to the last portion of this. What if I have a rational inequality? The same deal happens. So you can't cross multiply, even though you're so tempted to do that, because this is not linear. There's an x in the denominator. So what you do, you get everything on one side, 0 on the other side. It doesn't matter how you do this. Whether you move things to the left or the right makes no difference. You get a common denominator. So basically what you're doing, you're treating this like an expression. And that will be 4x minus 3 minus, if you distribute the -1n, minus x minus 4. This will be 3x minus 7 over x plus 4. And you do the same thing pretty much. What you do, you put a number line and you say, you know what, we could graph this again. We're going to graph this in the same chapter with polynomials. Where does this equal 0? At 7 over 3. Where does this equal 0? At -4. And you pick, multiplied or divided, you pick values just to see whether the value is positive or negative. If I pick -5, -15 minus 7 is negative. Negative 5 plus 4 is negative. 2 negatives divided will yield a positive. If I pick 0, 0, that will be 0 minus 7, that's a negative. 0 plus 4, that's a positive. And if I pick 5, 15 minus 7 is positive, and 5 plus 4 in the denominator is positive. And I want to know, where is this less than 0? Isn't less than 0 meaning negative? And these points are not included. So my answer here would be a negative 4 to 7/3. And if I do the same on the next problem, same deal. If I get everything on one side, again, you're so tempted to cross multiply, you can't do that. And they both have the same denominator. Minus 3 minus 1 is minus 4. Okay. I said minus 3 and I wrote a 3. Isn't that x minus 2, x plus 2 over x plus 6? So the work is the same. It really doesn't change much. And let me extend that line so that we have those fully separable. Here we go. And on the number line, 2, negative 2, and a negative 6. And if I pick a point right there, negative 6, negative 6 minus 2, negative 8. Negative 8 minus 2 is negative. Negative 8 plus 2, that's negative 6. Negative 8, 3 negatives will give a negative. Oh, by the way, this is greater than or equal. That's included, but that's excluded. Reason that's excluded, even though it's less than, greater than or equal, in the denominator you can never have a 0 in math. At least I'm in this class. You pick a point between negative 2 and negative 6. Let's say negative 3. Negative 3 plus 2 is negative. Negative 3 plus 2 is negative. And negative 3 plus 6 is positive. 2 negatives will yield a positive. I pick a point between negative 2 and, how about 0? 0 minus 2 is negative. 0 plus 2 is positive, and 0 plus 6 is positive. That's a negative. And in the last, I pick, let's say, 3. 3 minus 2 is positive, 3 plus 2 is positive, and 3 plus 6 is positive. So, since I want to know where is this bigger than or equal to 0, it's right there and right there. That would be from negative 6 to negative 2, union with 2 to infinity. And the last problem says, find the domain. Well, the domain is you take the radicand, the quantity that's underneath the radical, and you set it to be greater than 0, specifically greater than 0, or equal, right? Positive or 0. Well, isn't that 2x Does that work? Nope. I'm sorry. I should have worked with that. Let's see. So we're going to go for 2 and 2 didn't work. There we go. 4 minus 3 is the 1. We want a positive, so we want the 4 to be positive and the 1 to be negative. So one more time, I would have to really run a number line, and 3/4, negative 1 and negative 5. 3/4, negative 1 and negative 5. And if I pick a point in there, negative 6, negative, 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 that's a negative, 3 negatives. If I pick negative 3, negative, negative, positive, 2 negatives will be a positive. If I picked 0, negative 3, positive 1, 1 negative, and if I pick 2, positive, positive, positive. So where is this bigger than or equal to 0? It's right there and right there. Are those points included? Well, I can never include the denominator. But since it's greater than or equal, those are allowed. So my solution would be not including -5 to -1, union with 3/4 to infinity. And there's the homework.